Have you ever wondered how engineers are able to design complex circuits that power our phones, computers, cars? Want to know the secret? It all comes down to Kirchhoff's two laws. They explain exactly how current and voltage behave in complex circuits. Welcome everyone, I am Maciej Szewczyk, and on this channel you will learn how to solder and understand the principles that govern the world of electronics. Today is lesson 3 of our complete electronic course, where we will learn Kirchhoff's first law, also known as the current law. We will discover what happens to current at circuit junction and why what flows into a node must flow out. Pay attention because understanding this law helps you understand how current distributes throughout a circuit. I would like to remind you that this entire lesson is also available as an article on our website voltnova-labs.com. I encourage everyone to visit because there's a special simulator that will help you understand electronics more easily. Remember, our mission is to teach you electronics and soldering. If you want to join the Voltnova community and learn electronics and soldering with your own home laboratory kit, visit shop.voltnova-labs.com. First question: who was the scientist who invented this important law? His full name was Gustav Robert Kirchhoff, who was born just over 200 years ago, specifically on March 12, 1824. He came from the city's intellectual elite, which enabled him to obtain his doctorate at just 23 years old. Why so young? Imagine this. This genius invented the laws that bear his name at age 21 while still a university student. You heard that right. Laws. Plural because there are two Kirchhoff's laws. But today we will talk about the first one, the current law, as I mentioned. These aren't his only scientific achievements, but if you want to learn more, I encourage you to do some reading online or from other sources. We need to discuss what Kirchhoff's first law states. This is the fundamental principle. The sum of currents entering a node equals the sum of currents leaving that node. Remember this well. Write it down somewhere. I will explain everything and show you animations to make it easier to visualize. First of all, what is a node? A node is simply a connection point of at least two circuit elements, and on electronic schematics you can see it as a dot where components connect. Now we know what a node is. We know the definition of Kirchhoff's current law, so let's look again at what we wrote down. The sum of currents entering a node equals the sum of currents leaving that node. To put it simply, whatever current flows into a node must flow out of it. Let's look at this more closely. We have a node with current of 10 milliamperes flowing in through just one path, and it distributes into 4 different paths. For example, let's say we have 2 milliamperes here, 6 milliamperes here, 1 milliamperes here, and also 1 milliamperes here. The sum of these currents flowing out equals the current flowing in. As you can see, 10 milliamperes flows in and 10 milliamperes flows out, just split up. I will soon show you this in theoretical task, and we will of course support it all with practice. We can find new items in the back for this lesson. They don't have any amazing role in themselves. It's just the so-called gold pin, or in professional style, jumpers. At a later stage, I will tell you why this is in our circuits. The only thing you need to know right now is that when soldering these pins, remember they are just metal pins in a plastic housing. I mention this because you should not overheat the pins or you will melt the plastic and the whole thing won't hold properly. If you follow the rules I taught in the soldering theory, proper temperature and a soldering process that takes 3-4 seconds, you shouldn't have any problems. So try not to keep the iron on the pin for 10 or more seconds. However, if this does happen, and you melt the header pin, leave a comment and I will help you solve the problem. Of course, I won't mention resistors again. You already know how to measure their values. You can calculate it from their color bands or simply measure with an ohmmeter. Here's a quick tip for soldering pin headers. Insert jumpers into them before soldering. This will make it easier and reduce the chance of making mistakes. Let's analyze the first circuit from our kit. Get something to write with and refresh your knowledge from previous episodes about Ohm's law and resistor connections. This is essential to understand how Kirchhoff's first law works. First, we need to find the current flowing from the battery, the main current of the entire circuit. Our circuit from lesson 3 kit has two resistors connected. I'm sure the word is on the tip of your tongue, in parallel. So let's calculate the equivalent resistance of these two resistors. We know the formula, so let's plug into the values where R1 is 1k ohm and R2 is 10k ohms. The equivalent resistance is 909 ohms, meaning the battery sees a resistance of 909 ohms at its terminals. Now we can easily calculate the main current using Ohm's law. The formula is current equals voltage divided by equivalent resistance. I hope you are calculating this yourself. 9 voltage divided by 909 ohms equals 9.9 milliamperes. This is the current flowing from our battery. Here's what happens. The 9.9 milliamperes current flows and encounters a node. At this point, it splits into two parts, but exactly how much goes each way? We need to calculate this too. Current naturally takes the path of least resistance, more of it will flow where it's easier, meaning through the branch with the 1k ohm resistor. Here's a new term. A branch is the connection between nodes like here and here. Now forget about the equivalent resistance concept and return to the circuit with two resistors. We have a parallel connection, so both resistors have the same 9 volts across them. Because they are both directly connected to the battery, yes? The main current I splits into current I1 and current I2. The calculation method doesn't change, so in this branch I1 equals 9 milliamperes flows, and in this one I2 equals 0.9 milliamperes or 900 microamperes. Now add these current values I1 and I2 together. What do we get? The value of the main current flowing from our battery, 9.9 milliamperes. So let me repeat the definition of Kirchhoff's first law. The sum of currents flowing into a node equals the sum of currents flowing out of that node. The formula shown below the circuit checks out, but we will verify it in practice soon. While we are on a roll, let's calculate the second circuit. Below the circuit, it asks us to calculate the value of current I3 and write the formula for I, the main circuit current. We already know I1 and I2 since the resistor values are the same as before. The value of current I3 is simply 9 volts divided by 2k ohm, gives us 4.5 milliamperes, right? So, here's how it works. I is our current flowing in. Therefore, I equals I1 plus I2 plus I3. If there were a second current, let's say I4, also flowing into this node, we would write I plus I4 equals I1 plus I2 plus I3. So, you see, we don't need to calculate the equivalent resistance again to find the main current. Thanks to Kirchhoff's law analysis and writing out the current distribution formula, we know that I has a value of 14.4 milliamperes, which splits into 4.5 milliamperes, 9 milliamperes here and 0. milliamperes here, and the sum of these values is indeed 14.4 milliamperes. We have the answer to both problems. Now get your jumpers and multimeter ready because we are going to verify our calculations in practice. As you remember, measuring current with ammeter means connecting it in series with the circuit. We have 1 meter, but the schematic shows 3 ammeters. This isn't the time to run to the store and buy 2 more meters. This is exactly why we soldered the pin headers and have jumpers to short and open specific branches for measurement. Remember to never measure current with a jumper in place. Measurements should only taken where the circuit is open. Let's connect the battery and starting measuring. From our calculations, the current flowing from the battery to the circuit is 9.9 milliamperes. We need to short these 2 branches for a proper measurement, so let's check. Theory has been confirmed by practice. Now we open one of these but short our main lead. This also checks out. Now we just swap the jumper position and I can tell you in advance it will be the main current. I minus this current, but let's check. Everything checks out. We will not measure this circuit here. That's your task. Play around with it yourself a bit. There are no tricks here. Just check whether what we calculated matches in practice, exactly the same way as we just did. Remember to always disconnect the battery after measurements. No point wasting battery power. End of measurements, back to the studio. We have made it to the end. I hope you understood everything and that you will complete the task I left for you. Share your calculations and measurements, and if you have any problems with the task, write a comment and I will explain everything in detail. To summarize Kirchhoff's first law, remember that current naturally takes the path of least resistance. At a node, more current will always flow through the branch where it's easier, meaning where there's less resistance. I will also add that whatever current flows from the positive terminal of the power supply, the same amount returns to the negative. Even if there were 300 nodes and 600 branches with current splitting in all directions like lightning, at the very end, when it returns, the same amount will flow into the negative terminal as left from the beginning. Finally, if you want to purchase a complete electronics kit like this, the link is in the description. Thank you very much for watching. Subscribe and like, that way I know my mission of teaching electronics is on the right track. Bye!